Thank you for joining us today. My name is Erin Hoffman-John, and I am Head of Creative for Stadia Research and Development. I'd like to start by saying how personal the cancellation of GDC has been for our team. In the last 17 years, I think I've missed just one GDC. For many of us, it's the week that we set our calendars by, an event we depend on for our careers and for refilling the well of our connection with people who mean so much to us. So thank you again for joining us today. And we hope that you're finding ways to safely connect with each other in this very challenging time. I also would like to thank our event organizers here at Stadia and with GDC, who have poured their hearts into this event behind the scenes year after year. It is a privilege to share our work with the game development community, and none of this is possible without them. I came to Google 2.5 years ago after spending the last 17 years as a commercial game designer. I started in text-based games and have followed the arc of game technology innovation through consoles, MMOs, kids' virtual worlds, social games, mobile games, and more. Throughout my career, I worked on each of these emerging markets ahead of their time, and I came to Stadia because the prospect of distributed resources for games in the cloud seemed like the obvious next step in our progress as an industry. At Google, I co-founded Stadia Research and Development, a small team composed of veteran game designers and developers working closely with machine learning engineers and Google infrastructure engineers. You might be familiar with some of our work from the style transfer demo we showed at last year's GDC. Our goal is to bring the best of Google to game development. We do this by building relationships with some of the amazing technology teams inside of Google and creating experiential prototypes based on those technologies. Last year, we showed you some of the early promise of this line of work with our Style Transfer Art demo, and also our Stream Connect demo. We also presented our conceptual design for a new technology called GameBus, which would allow developers to connect the resources between multiple Stadia instances with sub-frame latency. Today, I'll be showing you the first light on these technologies working in real game settings. First, our project codenamed Chimera is a strategy card game powered by generative machine learning for art and ML agents for gameplay balancing and virtual opponents. Second, you'll see how semantic machine learning can power believable game characters without a single line of scripted AI behavior. Next, we'll show you how GameBus takes peer-to-peer multiplayer networking to a whole new level. Finally, we'll show the first proof of cross-instance resource distribution with a GameBus demo we call Ridiculous Soccer, computing complex AI behavior in a separate Stadia instance and weaving those instances together into a seamless experience. When we think about the potential of Stadia, one thing that virtually every developer we talk to is excited about is its potential to reach millions or even billions of new gamers. Today, there are more than 40 million Chromebooks in use in education alone, and Chromebooks make up over 20% of the commercial notebook computer market. These devices and the tens of millions of Pixel phones in circulation, added to the tens of millions of Chromecasts in the wild, are Stadia-perfect surfaces, and those numbers will only grow. Google products touch over 2 billion users in total. A platform built for accessibility across more than 1 billion existing potential users requires a new kind of thinking. How do we convert those users into the next billion gamers? And when those gamers arrive, how can we be ready for them? This order of magnitude increase in the potential high-fidelity gaming audience requires new approaches to game development. One of our most critical goals at Stadia Research and Development is to empower as many developers as possible to reach that potential massive audience. Enter Chimera, our experiment into applying machine learning to every aspect of the game development process. Our goal with Chimera was to create what some have called human-AI centaurs, a seamless partnership between human and machine, the combination of which is greater than the sum of its parts. Advances in machine learning have shown us clearly that the next leap forward in technology comes from empowering people with machine learning tools. So what does that mean when you apply it to game development? One of the biggest problems in game development is rapid, often repetitive content generation. A game in development wants to be fluid and iterative, responsive and agile. But when the work of hundreds of people depends on a fixed target, iteration slows, and so does innovation. In 2019, we showed a vision for a rapid visual ideation process made possible by artistic style transfer applied to real-time game graphics. But we wanted to go further. We wanted to go beyond the post-processing layer and into generating game art itself. So that's what we did. First, we thought about what an explosive quantity of instantly generated game art might make possible. Virtually every developer who has shipped a game has experienced having to cut or cut back a feature because of its art requirements. So we turned that limitation upside down and said, what would we do if there were no limit on the kind of 2D assets we could generate? Creature breeding came to mind, but of a kind not possible in the real world. What if we could combine animals arbitrarily and keep combining them? The chimera concept was born. We knew that generative adversarial networks had been used to generate images. Andeep Toor, one of our machine learning engineers, demonstrated a version of the technology and argued for applying it to the game assets. His early experiments proved promising, so we went all in on creature combination asset generation and the generation of backgrounds for behind those creatures. A machine learning model is nothing without the data it's trained on. The most impressive image generation relies on tremendous amounts of common data, such as human face photographs or landscape photography. By definition, what we were attempting to do had no basis in existing data. If it did, the problem wouldn't be nearly as interesting or as applicable to games, which are usually creating artistic works of fantasy. For the landscapes, we began with licensed sources of landscape photography. For our final backgrounds, another of our ML engineers, Trung Lee, produced a style filter that softened the edges of the backgrounds while giving them a brush-like effect. We wanted to evoke a sense of the biome the creature would live on, but not overwhelm the card with landscape detail. And that brings us to the creatures. We began by training on a large animal dataset. Even though we knew it wasn't likely to produce the results we wanted to prove that it couldn't. So we trained a network on a large animal photograph dataset and produced these animals. Some of them are pretty cute, but they definitely didn't have the drama we wanted for our epic card game. So we had to generate our own data. Our technical artist, Lee Dotson, collaborated with our machine learning engineers to create turnarounds of 3D animal models, essentially procedurally generating a massive image dataset. By looking at the gap between our initial photographic animal test and the kind of dramatic portraits players expect in card games, we were able to design the parameters needed for our dataset, characteristics we needed to create a dramatic presentation. The animal had to be posed dramatically, not, for instance, like the standard image of a cow in a field, or the kind of animal reference you can commonly find on the internet. The model had to be dramatically lit, usually from above, and the camera had to be zoomed in and angled just right. Once trained on this dataset, we could generate a novel animal that did not exist. Animals very like it existed on our dataset, but there was no exact match. All of the animals you see here are generated by our conditional generative adversarial network system, then pass through a procedural style filter. The backgrounds are generated as well. But creating convincing animal cards was just the beginning. Now we needed to combine them. This also proved uniquely challenging. When we just let the machine do the work, it created a kind of average of all creatures that became indistinguishable, and also had the tendency to spit out what the team referred to as nightmare fuel. We knew we needed to give the artists more control. Ultimately, we took a two-pronged approach. In one approach, we collaborated with a team in Google Brain to produce the Chimera Painter, an artist tool that could be used to paint segmentation maps that a conditional generative model could fill in. Then, applying our procedural approach, we used Houdini to combine parts of the 3D models and render them in vector color to procedurally generate the segmentation maps, then combine them. This didn't produce perfect results, but it got us 80% of the way there, and also produced general shapes that the model was better at recognizing. One important part about the way this generative model works is that we're not telling it what animal to put where. It's deciding what animal to use based on what silhouette it sees in the segmentation map. The result of both approaches eventually produced creature combinations that were convincing, dramatic, and machine-generated. Here are a few of our favorites that came out of this system. There are literally thousands more, but we'll have to keep going. Here you can see the final card composition, where we're taking our generated landscape, laying it behind the chimera, and unifying both using procedural filtering. This allows us to reach the card combinatorics we were looking for in allowing players to combine any creature in the game to create hybrid game pieces. Once we had this amazing ability to generate thousands of creature combinations on demand, we had a different problem. How do you design for such an explosively complex system? Just as every developer knows what it's like to cut a feature based on art budget, every strategy game player knows what it's like to play a game that has gone out the door with a game-ending exploit in its design. From a designer standpoint, it can be a lose-lose situation. Either you design the game to be simple enough that you can predict all outcomes, and it's boring, or you design the game to be so complex it isn't realistically feasible to predict all of those edge cases and combinations. Generally, the balance of a complex game with many interrelated dynamic systems is a problem broached only by large, well-resourced teams with dozens of designers. We wanted to tackle it with one. There is some precedent for using neural networks to assist in game balance. In 2018, Teresa Duringer gave a terrific GDC talk called Race for the Galaxy, a Neural Network in Production, which walked through the process of using temporal difference learning to evaluate board states. This approach is fascinating and clever, and promising as well in how it hybridizes machine learning with traditional AI scripting. For our purposes, it was important that we didn't use any hand scripting in the machine process, because we wanted flexibility in trying different game rules, so we trained a single network to play the entire game. We also wanted an explosive combinatorial system involving the merging of not just visual assets, but of their underlying game behaviors. This meant we had to take an unsupervised learning approach, an agent that learns through self-play. It put us more in DeepMind territory. However, as with real-time artistic style transfer, the unsupervised learning community was skeptical we could pull it off within reasonable compute limitations. Magic the Gathering, for instance, a game whose combinatorial complexity was closer to our ambition, is famously considered impossible to solve with AI. We ultimately arrived on a hybrid solution that used a data-driven game simulation architecture designed by our UX engineer, Maxwell Hanneman, to generate all playable moves in the system, then paired this with a reinforcement learning agent trained on millions of playthroughs of the game. Here are some analytics that came back from those millions of playthroughs. You'll notice that one of the exploits I mentioned, on their own, the agents found a degenerate strategy by applying the dodge power-up to the Tyrannosaur. I knew that the T-Rex was strong, and I knew that I wanted it to be the strongest creature in the game, but something this OP is just not fun. So we made some adjustments, a series of adjustments as you do with these things, that preserved the intent of the Tyrannosaur, which was to keep it big and frightening, but brought that curve back under control. Ordinarily, this kind of thing might not be caught until the game could be played by hundreds of real people. But because I now had access to agents who could play the game tens of millions of times after every change I made to the game balance, I could progress through that system iteration much more freely and quickly, without needing access to hundreds of playtesters. It was also fascinating to me how, as a designer, I could look at these analytics and see creative choices that I'd made in the balance of the game, often fluidly and intuitively during the initial prototyping process as I built the cards, reflected back to me in the analytics. I'm used to this when working on a live game with thousands or millions of players, but it's quite a trip to see this data before anyone outside the team has played the game. So let's look at it all together. During gameplay, I have a hand of cards and can begin playing the game by placing biome tiles onto a common board space. These biomes can be expanded upon or evolved into new kinds of biomes, and creatures in the game, represented by cards, have different biome requirements. My chimera begins as an egg, but in this case I've evolved it once already by absorbing a bat. I'm going to merge it now with one of the creatures on the board, the Tyrannosaur. When I absorb a creature with the chimera, the absorbed creature's abilities are translated into new abilities for the chimera, as are the creature's stats. So we can see here the resulting double chimera, half bat and half Tyrannosaur. I could absorb any of my own creatures here, but I think I'll pick up the hyena. I can also attack any of my opponent's creatures with my own creatures, or play spell cards that have direct effects on any entity on the board. So the strategy space of the board game here is exponential, especially as the board increases in complexity during play, and as I make decisions about what kinds of abilities I want my chimera to have, and what kinds of creatures I can support on the available biomes. Meanwhile, my opponent is an ML agent, and it's deciding on a turn-by-turn basis what the next best move is. I have to say, after playing this as much as we have, it becomes evident that the game is just hard. There's a lot of depth due to all the combinations, and we definitely get that unsettled gut feeling from watching how good the ML is at playing this. It knows, without us having explained to it, that it definitely wants to place all of its creatures on the board, and it also wants to enhance as many of its allies as it can with special abilities. It makes it extremely interesting to watch what it chooses to do. Now, the thing with an unsupervised learning agent is that you don't necessarily know why it's making the choices it's making. This is called legibility in ML terms, and we wanted to get some insight into the decisions that the agent was making. So one of our ML engineers, Shufan Zhu, worked with our ML team to create an interface that would let us see what the machine was thinking at any given moment. In gameplay terms, this is an automated coach, but again, we didn't script any of it. I can click a hint button and it will give me a recommendation of 3 moves along with the estimated game win probability associated with each. I can also check a graph to see how the machine thinks I'm doing in the game overall and over time. Now let's say I decide not to do what the machine says and make a few moves that I know are bad. In this case, I'm going to buff one of my opponent's creatures and then buff one of my own. If I check the graph again, we can see the ML was not impressed with the first choice I made, and then things got a little bit better and then they got worse again. What's next for us with this work is really to let the agents loose and bring together these threads of game balance and game agent play. Our goal was a game that would allow the machine itself to build decks and to personalize those decks to the skill level of the player based on what its estimate of the player's ability was, because that graph is also measuring the player's ability as they play. What's clear to us thus far is that these methods show significant promise in increasing the reach and potential of game development teams. If you'd like to find out more about each of these projects, we'll be releasing a series of blog posts on stadia.dev where you can dive a lot deeper. Now we'll show a technology that attacks the same problem, saving developers time by bringing machine assistance into the game development process. In this case, the technology is semantic machine learning, and specifically a model trained by our colleagues at Google AI. Semantic machine learning models are trained on massive data sets of language and create multidimensional graphs of the relationships between words used in those data sets. Anna Kipnis describes this application of semantic ML coming from her 17 years of experience as a narrative and gameplay programmer at Double Fine. She recounts infinite-seeming hours spent scripting for every possibility of a player's interaction with an NPC. What you're about to see in her Verb World demo has zero AI behavioral scripting. A journalist recently described this demo as granting our fondest secret wish, to talk to an adorable fox. I'm pretty sure it was Anna's not-so-secret wish. In this, the player can type whatever they want to the fox. For instance, saying hi to everyone and it'll wave back, or asking the fox for some coffee. When asked, the fox brings a small mug to the player. Again, it has not been told to do this. It used semantic ML to connect the request of coffee with the nearest related objects, in this case the mug, and then brought it. We don't leave this purely up to the free association of the machine, however. Anna has built a developer tool that allows a designer to alter the categories of responses the fox might have to things. This is a bit more like behavioral scripting, but radically simpler, since it's just interpolating between very broad commands. So in this case, she's used it to create 2 different foxes with different personalities, one happy and one sad. Note how the foxes respond quite differently now to the same commands or interactions, and how this shows personality. Anna describes this as giving the fox a rich inner life, that mysterious sense that the best AI-driven games have and give us that the game characters are alive. For more on this technology, keep an eye on our blog at stadia.dev for a deeper dive into Verb World with Anna Kipnis. To check out the semantic technology, our friends at Google AI have created a tool called the Semantic Reactor. It's a Google Sheets add-on you can use to experiment with language models. It's available as an experiment within the Google Cloud AI workshop. Check the description of this video for a link, and we'll also link it from our upcoming blog post. Now we'll take a step back from the magical but often head-spinning world of ML and into the distributed compute resources for games with sub-millisecond latency. If you need a snack, the great thing about a virtual conference is you can pause the video. The first demo we'd like to show you uses the proximity of Stadia instances in the cloud to take peer-to-peer multiplayer techniques to an entirely new level. Our development partners and friends tell us that one of their biggest challenges is multiplayer networking, and we know well that it's generally just not a fun challenge. When you get it right, it's invisible to the player, and when you get it wrong, rage ensues. So one of our senior engineers, Michael Todorovic, set out to figure out what game bus message passing technology could mean for multiplayer game networking. What we have is another early proof of a pretty promising idea. What you see is Guilt, the beautiful narrative game from Tequila Works. Those familiar with Tequila Works knows that this studio excels in artistic sensibility, storytelling, and puzzle design. They have never launched a multiplayer game. So what if we could take their game and seamlessly transition it to multiplayer? Michael had a theory that the proximity of Stadia instances in the cloud would mean that peer-to-peer approaches to networking could have new potential. By distributing the player connections differently, we could produce a scalable solution that was a fundamentally different kind of multiplayer networking architecture. That would mean a technology that could go from 2 players to 1,000 players seamlessly and elegantly. We wanted to prove that this could work even with games that had never been designed for multiplayer, so we asked Tequila Works if we could borrow a couple of Sallies. We built a peer-to-peer networking system that could connect to GameBus, and then placed some simple hooks for the relevant data into Guilt. What you see is the end result working here. Naturally, the question is, how many players can this support? For that answer, we have to turn to simulation and to the architecture. Ordinarily, a major challenge with multiplayer is round-trip latency between the client machine of one player, the server, the client machine of the second player, and back again. The further apart the links in the chain are, the higher the latency, and subsequently the probability of poor experiences, desyncs, or errors increases. Reconciliation of these errors, situations where either of the clients or the server has a different picture of reality than the others, is one reason why multiplayer networking is so difficult. With Stadia, the proximity of the client instances in the cloud allows us to take away the intermediary and use a serverless architecture with unprecedented scalability. When we calculate bandwidth per second needs for this architecture, we're confident in reaching 1,000 simultaneous players without desyncs or perceptible loss of quality. In the future, with improvements in hardware and firmware, this number should only grow. Instance proximity, of course, is just the beginning, even when it comes to leveraging it for new multiplayer technologies. In 2019, if you caught our vision for game design in a streaming future, you will have seen our early conceptual diagrams for a technology called GameBus. GameBus is named for the message passing bus inside a computer, but in our case, we're passing messages of arbitrary size, and not just within a machine, but between them. Sometimes those machines are side by side in a rack, and sometimes they're not. GameBus is the transport that allows us to pass chunks of data large enough to meet game development needs between resources in the cloud. Because of Google's unique cloud infrastructure, we can pass this information with subframe latency. This is the first demonstration of GameBus working in a game context. You see here 2 teams playing soccer. Unlike Chimera, this is a traditionally scripted game AI system. We wanted to show something practical and beefy. These scripted agents have a lot to keep track of: where the ball is, where their teammates are, where the goal is. They work as a team, and the members of the team have roles as they would in a real soccer match. If we drop a few more balls on the screen, the work the agents need to do increases. You can see here that the compute load is pretty low. Our interface on the right shows you what parts of the game consume various quantities of resources. These are bowls running through. Right now, our AI load is low because we have so few agents on the screen. But what if we add some complexity to the environment? The AI task starts to increase in complexity. And if we add more balls and more teams, it increases even further. And you can see that load starting to go up. More bowls. More bowls is always the answer. Now we can see that we're beginning to hit the limits on even what a quite powerful Stadia instance can provide. If we continue to pile on load by adding even more teams, we can see the frame rate drop as the compute resources are totally consumed by the complexity of the aggregate AI being taken on by the processor. But because we're in the cloud, we can take advantage of adjacent resources and simply rebalance them inside the rack. If you watch the columns on the far right of the screen, you're seeing them take that resource load off the column on the left in real time. This is GameBus. Now I'm seeing the frame rate pick back up again, as the other resources naturally balance the load being distributed to them by the parent instance. The game is running smoothly, and I can continue to add more units to the game without taxing frame rate. The combined power of the instances you see here is simply not possible on any other platform, and yet these are resources we're able to access readily on Stadia. Thinking about the potential of game bus and distributed real-time compute for games is to think about the architecture and capability of games in a whole new way. We wanted to demonstrate this to you today to spark the beginning of a new kind of thinking about game resources and what we would do with them if the boundaries we're so accustomed to could be lifted. GameBus is the reason why we continually ask developers where they're hitting the limits on their current platforms and what barriers they just aren't able to break today. This is just the beginning for GameBus. We're excited to show you the first look at the technology working, but we're even more excited to hear your ideas of what to do with it. Our next steps with this approach include expanding our AI service to NavMesh navigation and then real-time physics. Thank you very much for tuning in for our research and development update. If you have feedback for us on what you've seen today, we hope you'll consider filling out our developer survey. You can find it linked from this video and also linked from our blog post at stadia.dev. Over the next few weeks, we'll be releasing articles that delve deeper into each of these technologies, along with links to how you can begin experimenting with them on your own. Thanks again for watching, and we hope to hear from you soon.